Hey guys, it's Alex and Joyce from Teaching Growth, and today we're going to be teaching you the first two parent functions, which are the squared and cubic functions.
So the first function we're going to be going over today is the squared function. And the squared function is denoted like this. F of x equals to x squared. Now, the f of x notation simply means that the function f, the squared function, is dependent on the variable x. And what does dependent on the variable x mean? It just means that the variable x is in the equation for the function. So what a squared function means is that it would be x multiplied by itself, basically two copies of the variable x. So to show you what I mean, I'm going to do a quick table with values of x. Now, I think the easiest value to start off with may be 0. So 0 multiplied by itself is still 0, so it'll give you 0 as output. Now we're going to do this for a couple of numbers so that way we can graph the points on the graph so we can show what the function actually looks like. We're going to start with -1 and 1. The reason I'm pairing these two is because I think it's important to show that even though the inputs are different, -1 and 1, they still have the same output in squared, because when you multiply -1 by itself, the negatives cancel out and it'll still give you a +1, right? So we're going to go down the line for a couple more of these paired numbers. So we're going to have -2 times -2, negatives cancel out, gives you 4. 2 times 2 is 4. And we can do -3 and +3, which will give you 9 and 9. Now, when we graph these, well, this graph has every tick mark at every 2, like every number 2 unit. So we're going to be graphing it like this. So we have 0, 0. We have +1, +1, -1, +1. Our next numbers will be -2 and 4. So -2 is the tick mark, and +4, +2 and 4. Then we have 3 and 9, and -3 and 9. So what you'll start to notice about the graph is it has this distinct shape. This curved shape is distinct to most polynomial functions. Polynomial simply means it's going to be the variable that depends on the sum power, but this specific shape is for the squared function. Now, what we're going to talk about first is something called intercept, and the most important point to note for a squared function when talking about intercept is the point 0, 0. Now, what does the word intercept mean? So when we talk about intercept, we're talking about the x-axis and the y-axis. Whenever a function crosses each axis, that would be the intercept. So at this point would be the x-intercept, and at that point would be the y-intercept. So where would be the x and y-intercept for the squared function? Well, 0, 0 would be the y-intercept, because at this point the graph crosses the y-axis, and you may be thinking, okay, 0, 0 is probably also the intercept for the x-axis then. But that's not true, because in this case, the function doesn't cross the graph. It bounces off the graph in an inflection. So in this case, we don't call it an intercept. We'll be learning more about this point later, actually. So we can write that down really quick. Our x-intercept does not exist. And our y-intercept is at 0, 0. Okay. Now, the next aspect of this graph I want to talk about is the domain and range. What domain is essentially all values of x that this function can exist on in this graph. So x, or domain. Right. So what values can this graph exist on? The answer is in basically -infinity to +infinity, because we don't have a restraint on the x. There's no reason why you can choose both positive and negative numbers. You can choose decimal numbers, you can choose fractions. So x is not limited to anything. And the way we write that is we write x is a subset of all real numbers. Now, of all rational, or Yeah, of all real numbers, sorry. So what this symbol means is basically x belongs in this category. And I'm not going to go into too deep what this r means, but it essentially means all numbers that can you usually see on a timeline. And we'll be going over into subsets of numbers in future videos. Now, moving on to the range. The range isn't as free as a domain for the squared function in this case. If you notice on the graph, everything is above the x-axis, right? Everything is above there. Nothing can exist below the x-axis. And what that means for the range is that x has to be greater than or equal to 0, because we can't have a negative number as our range. Because remember when we were talking about squared earlier, whenever we have a negative number, it squares and it becomes a positive, and so we don't end up not having a negative output. Now, the next aspect I want to go over is symmetry. The squared function has symmetry over the y-axis. That's pretty easy to see. If you imagined a dotted line down the y-axis, if you flipped each side over, they would mirror each other. So therefore it has symmetry over the y-axis. Now, the next one we're going to go over is going to be maximum and minimum. Now, there isn't going to be a maximum for this function for the reason that it isn't bound as it continues going, right? Remember when we said our x wasn't bound, so as our x increases, we can have like infinitely increasing y or f of x output as well. So for a maximum, you can put does not exist. And we usually put does not exist instead of infinity, but that's also a valid answer in this case, since as x reaches infinity reaches like positive infinity or negative infinity, the y will also reach infinity on the y-axis. Now, but for the minimum, in this case, there definitely is a minimum. Since it can't go into the negative, it can't go into the negatives for the y-axis, what's going to happen is that the minimum value is actually going to be 0, since 0 as in the y-axis. Whenever we talk about maximum minimum, we're talking about outputs, just to clarify. And those should be all the aspects that you need to know about the squared function.
So the next function that we're going to be discussing is called a cubic function, and it can be written as f of x is equal to x cubed, or x to the third power. And that's why we call it a cubic function. And just like Joyce has said before, f of x simply means that we have a function f that's dependent on the variable x. So what exactly does a cubic function do? Well, just like a squared function, you really got to look at the exponent here. And what this exponent does is it tells you how many times the base, which is x in this case, has to multiply itself in order to get its true value. So for an example will be 3. Let's say x is 3, so we're going to have 3 to the third power. What this function will be doing is returning a number that multiplies by itself 3 times. So 3 to the third power will be 3 times 3 times 3, which is 27. So in order to get a basic idea of what this graph is going to look like, we're going to write a table out labeling f of x and x. And to get a basic idea of what this function might look like, you're only going to really need 5 points. And those 5 x values that we're going to be using are -2, -1, 0, 1, and 2. So if we were to input -2 as our x value, in return for f of x, we would get -8 as our answer, because -2 times -2 times -2 will get us -8. And if we were to input -1 as our x value, it would return to us -1, because -1 times -1 is +1, but multiplied by another -1, we get -1. And I'm sorry if that was confusing, that is a lot of negatives. So if we were to input 0, we'd get 0 returned. If we were to input 1 as our x value, we'd get 1 returned. And if we were to input 2 as our x value, we'd get 8 return. So what we're going to do is we're going to take these values and we're going to plot them on the graph. And like with Joyce's graph, every tick that we see is going to represent units of 2. So the first point we're going to graph is -2, -8, and it will be located approximately right here. I'm sorry, down here. The next point we're going to graph is -1, -1, and it will be right here. The next point 0, 0, which will go right here. The next point is going to be 1, 1, which will go right here. And the final point, which is 2, 8, will go over here. So if we were to take these points and connect them with a line or use infinite amount of points, our function would look like this. And this is what a cubic function would look like. So a feature that we're going to be talking about for the cubic function are its intercepts. So like Joyce had said before, an intercept is basically whenever the function crosses either of the axes. So if we look here, we will notice that our graph or the function, the cubic function, actually passes through the origin and it crosses. Whenever our function crosses through the origin, we know that it's going to have not only a y-intercept but also an x-intercept as well, because we see that it crosses both the x and y axis. So when we are to write this out, for me, I'm going to write x-intercept. Int is going to represent intercept. So when we write the x-intercept, we write 0, 0. And for the y-intercept, which I will abbreviate as y-int, we write the same thing, which is 0, 0. So because this function crosses through the origin, we're going to have an intercept in both the x-axis and the y-axis as well. So the next feature that we're going to be talking about for the cubic function is symmetry. And something that is unique to cubic functions is that they are symmetrical to the origin. So essentially, if you were to take this function and you were to flip it across both the y and the x-axis like this, we would get the same exact function because it is symmetrical to the origin. So this is a feature that's unique to cubic functions and a few more. So the next feature that we're going to be talking about for cubic functions is domain and range. And like Joyce has already said before, domain are the possible x values that we can have for a certain function. So I'm going to write domain for d as d here, and we're going to be discussing only x possible values. And this function can have any x value that it desires that are real numbers. So it can go and approach negative infinity and approach positive infinity in terms of x because it can have any input value for x. So the way we write this is we say x, write this, and this. And like Joyce has said before, x basically belongs to a set of real numbers. So x can take any real number value that it desires. So the next thing that we're going to talk about is range. And range is similar to domain, except it discusses y values. So it's a set of possible y values or f of x values that this function can have. So cubic functions can go from negative infinity to positive infinity as well. There are no restrictions, unlike the squared function. So we can write this as this, which tells us that y can have any, or this function can have any y value because there are no restrictions onto this function. So the final topic that we're going to discuss, or attribute, for the cubic function is maximum and minimum. So something that you will realize after looking at range is because there are no restrictions to the y value, we technically do not have a maximum or a minimum y value because both approach positive and negative infinity in terms of y. So for that reasoning, what we can write is for max or min, for max or min, we can write that it does not exist, and this can be notated with the D and E right here. So there is no possible maximum or minimum value for y. So for this, we write that it simply just does not exist. And this is everything that we have to discuss about cubic functions.